We're given a tank in the shape of a cuboid being filled with water. The dimensions are shown, and we're told after t minutes the height is h and the volume was v. Modeling the situation, so the sides have negligible thickness, and the rate of change of v is inversely proportional to the square root of h. Let me write that one down then. So the rate of change of v is dv by dt. This is proportional to 1 over root h. What that means is dv by dt is going to equal k over root h. And that is our constant proportionality. We're asked to show, in fact, the rate of change of the height. So for this, I can use the chain rule. I can say that dh by dt is going to be dh by dv times dv by dt. So my connected rate of change. Now, v is going to equal the volume of the liquid. So it's going to be 20 times 10 times h. That's the little cuboid that the water makes. So 200 h. And therefore, dv by dh is simply 200. Now we actually want dh by dv. That's just 1 over dv by dh. So dh by dv is 1 over 200. And we can finally bring it all together. It's going to be 1 over 200 multiplied by k over root h. In fact, this becomes precisely lambda over root h, where lambda is going to be k over 200. You could, there's a couple of things you can do, but if we're times them by 1 over 200, we can just times the top by 1 over 200, giving us k over 200, or you could keep change flip. So you're actually dividing by 200, and then you can just divide the top. But anyway, that's what we end up with. So dh by dt is lambda root h as required. Right, now given that the initial height was 1.44, so that means when t is 0, h is 1.44, and exactly 8 minutes after the water started flowing, so that's when t is 8, the height was 3.24. Use the model to find an equation linking h and t, giving our answer in this form. Okay, well, we want to integrate essentially. We've got the rate of change of the height with respect to time. It's actually in terms of the height. We can't just integrate because the height is a function of time. So we need to first of all do separation of variables. I'm going to multiply through by the square root of h. And I'm also going to write it as h to the half because that's going to be more useful in a minute. Now we're going to get a plus c in a minute when we integrate. And we've also got this lambda, but we've got these two conditions to sub in and help us figure out those amounts. So there's a couple ways we can do this. The way that I like to do it is I just now take this as it is and integrate both sides with respect to t. Using the chain rule, this actually becomes dh. You might alternatively have learned to times through by dt and then kind of stick an integration sign. We get to the same place. Integrate the left-hand side with respect to h. That will become h to the 3 over 2. Divide by that new power, so 2 over 3. And that is going to equal lambda t plus c. Okay, we've got ourselves an equation, and it's looking a lot like this. We just need to sub in some values now. So let's go with t is 0. Then remember the height was 1.44 then. We can use our calculator. So I decided to keep the 2 over 3 on the left for the moment. I know we're going to have to times through by it eventually, but I just thought let's go with it. So 2 over 3 times 1.44 to the power of 3 over 2 is 1.152. And that's actually going to equal c because t is 0, so the lambda t just disappears. Nice. So let's just update. We've got 2/3 h to the 3 over 2 is lambda t plus 1.152. Okay, and now I'm going to sub in that second condition. T is 8, H is 3.24. Okay, so this time got 2/3 times 3.24 to the power of 3 over 2. That gives me 3.888, which is going to equal 8 lambda plus 1.152. Of course, then I can minus and divide by 8, which gives me 0.342. And hence, oh, I'm not quite there. Right, we've got a couple of more lines. So 2/3 h to the 3 over 2 is therefore 0.342 t plus 1.152. So now I'm going to times through by, we can times by 3, divide by 2, or just times through by 3 over 2. So I'll do it for this one first. Okay, 0.513. And the second one, when you do it, you get, I'm just going to tell you, we get 1.728. You can give your answer as a fraction, but I don't know, it's a model and everything. I think it's more useful to write it using decimals. In fact, um, you, you might even round it to 3 significant figures because we're doing a kind of a modeling situation, but we're okay to leave it like this. Then finally, hence find the time taken from when the water started flowing into the tank, that was when t is 0, for the tank to be completely full. Now, let's just take a look at that tank again. The height of the tank was 5. So that's what I need to set h equal to. And then I'm going to solve for t. So 5 to the 3 over 2. And we can work that out on our calculator. Minus the 1.728, divide by 0.513. And we end up with t. This, by the way, ends up being 11.1803. So t becomes 18.4256, or to 3 significant figures, 18.4 minutes. It doesn't ask us to give it in minutes or seconds, so I'm just going to leave it like that. Nice. So connected rates of change question that has led us to a differential equation, which we've used separation of variables to solve, and then substituted values in to get the unknowns. And then finally, once we've got our equation, worked out how long it takes for the tank to fill up. Okay, well done.